warahmatullahi wabarakatuh. Salam sejahtera bagi kita semua. Om Swastiastu, Namo Buddhaya, salam kebajikan.
Honorable lectures both for mining engineering and biology education, the honorable speaker, distinguished guests, ladies and gentlemen.
Yang terhormat para dosen dari program studi teknik pertambangan dan pendidikan biologi atau yang mewakili, dan yang terhormat pembicara dan hadirin dan hadirat yang berbahagia.
On behalf of the organizers, we would like to extend a warm welcome and express our gratitude for participating in this international public lecture of the Permian and Triassic exotic blocks of Timor.
Atas nama penyelenggara, kami ingin menyampaikan sambutan hangat dan mengucapkan terima kasih atas partisipasi hadirin dan hadirat dalam kuliah umum kali ini.
Ladies and gentlemen, this international public lecture, proudly presented by Mining Engineering Study Program in collaboration with the Biology Education Study Program.
Hadirin dan hadirat kuliah umum internasional. Kuliah ini dengan bangga dipersembahkan oleh Prodi Teknik Pertambangan yang bekerja sama dengan Prodi Pendidikan Biologi.
Therefore, the theme for this international public lecture is the Permian and Triassic exotic blocks of Timor. This event intends to share knowledge about the Permian and Triassic exotic blocks of Timor, which will be delivered by a prominent speaker.
Oleh karena itu, tema kita pada hari ini adalah The Permian and the Triassic exotic blocks of Timor, dengan tujuan untuk mengetahui tentang blok Timur pada era Permian dan Triassic yang akan disampaikan langsung oleh pembicara terkemuka.
And to begin with, allow me to read the agenda for our opening ceremony.
Dan sebagai permulaan, izinkanlah kami untuk membacakan agenda upacara pembukaan.
First is the listening of the Indonesian national anthem and then followed by an opening prayer.
Yang pertama adalah mendengarkan lagu kebangsaan Indonesia Raya, kemudian dilanjutkan dengan doa pembuka.
Second is the welcoming speech from the chairman of the committee.
Yang kedua adalah sambutan dari ketua panitia.
Third is the speaker introduction and followed by a presentation of the material by the speaker, and then followed by question and answer session.
Yang ketiga adalah pengenalan pembicara yang akan dilakukan oleh moderator dan dilanjutkan dengan pemaparan materi dan pembicara yang akan dilanjutkan dengan sesi tanya jawab.
Fourth is handover souvenirs.
Yang keempat adalah penyerahan cindera mata yang kemudian dilanjutkan dengan kata penutup oleh Ketua HMP Pendidikan Biologi.
Fifth, closing prayer and then followed by photo session.
Yang kelima adalah doa penutup dan kemudian dilanjutkan dengan sesi foto bersama.
The honorable distinguished guests, ladies and gentlemen, to honor our country, please let us all rise for the listening of the Indonesian national anthem.
Hadirin dan hadirat yang terhormat, untuk menghormati negara kita, marilah kita semua berdiri untuk mendengarkan lagu kebangsaan Indonesia Raya.
you, please be seated.
Terima kasih hadirin dan hadirat, dipersilakan duduk kembali.
Next, opening prayer.
Selanjutnya adalah doa pembuka.
Sebelum memulai acara kita, marilah kita menyiapkan hati dan batin kita untuk berdoa. Izinkanlah saya membawakan doa ini sesuai ajaran agama Katolik. Dalam nama Bapa. Sebelum mengawali webinar kita pada hari ini, marilah kita semua sebagai manusia yang beriman menundukkan kepala kita dan menghadap Tuhan dalam doa. Kita awali doa kita dengan tanda kemenangan Kristus. Selamat sore Allah Tritunggal yang Maha Kudus, Allah Bapa, Allah Putra, dan Allah Roh Kudus. Puji serta syukur kami haturkan kepadamu, karena Engkau masih memberikan kami semua nafas kehidupan hingga saat ini. Terlebih khusus untuk penyertaan-Mu, sehingga kami dapat berkumpul kembali di tempat ini guna melakukan kegiatan kuliah umum kami dengan tema The Permian and Triassic Exotic Blocks of Timor. Ya Allah yang Maha Bijaksana, jadikanlah kuliah umum hari ini sebagai wadah ilmu yang bermanfaat bagi kami semua, terlebih khusus untuk pendidikan kami selanjutnya. Untuk itu ya Tuhan, berikanlah kami berkat dan Roh Kudus-Mu agar kami dapat menjalankan kuliah umum kami hari ini dengan baik. Jadikanlah kami yang mengikuti kuliah umum hari ini sebagai generasi yang kuat di masa depan, yang dapat bermanfaat bagi diri sendiri, keluarga, masyarakat, bangsa, dan negara kami. Akhirnya ya Tuhan, kami sampaikan segala doa dan permohonan kami ini lewat perantaraanmu Tuhan kami Yesus Kristus. Amin. Dalam nama Bapa dan Putra dan Roh Kudus.
Ladies and gentlemen, now we move to the next agenda. It is the welcoming speech by the chairman of the committee. For the chairman, the time is yours.
Agenda selanjutnya adalah kata sambutan dari Ketua Panitia sekaligus dengan resmi membuka kegiatan kita pada sore hari ini. Kepada beliau waktu dan tempat dipersilahkan.
Assalamualaikum warahmatullahi wabarakatuh. Selamat sore, salam sejahtera untuk kita semua, salam kebajikan. Mungkin saya tidak perlu memperpanjang kata lagi. Dalam sambutan kali ini hanya dua ucapan yang dapat kami sampaikan saya selaku Ketua Panitia mewakili panitia. Yang pertama, ucapan terima kasih kami ucapkan kepada pemateri kami pada sore hari ini, Prof. Hugo, yang dimana dalam waktunya yang padat melakukan penelitian di daerah kita, beliau masih sempat menyisihkan waktu untuk membagi ilmu, membagi pengetahuan kepada kita semua, khususnya mahasiswa program studi teknik pertambangan dan mahasiswa program studi pendidikan biologi. Ucapan terima kasih juga saya utarakan kepada HMP Biologi yang dimana telah bersama-sama menerima uluran kerjasama dari HMP Teknik Pertambangan. Sebelumnya di sini saya memberitahukan kami ada mau kerjasama dengan FST Biologi, namun dari sana ada kendala, jadi kita hanya 2 program studi. Sebetulnya harus ada 3. Selanjutnya ucapan terima kasih juga saya ucapkan kepada peserta yang dengan antusias, dengan partisipasi yang tinggi datang untuk mengikuti kegiatan kuliah umum pada sore hari ini. Ucapan terima kasih yang terakhir kepada semua panitia yang telah berkontribusi dari pra kegiatan selama kegiatan ini berlangsung sampai dengan kegiatan ini berakhir. Ucapan yang terakhir yaitu ucapan maaf. Di sini saya mewakili panitia mengucapkan permohonan maaf bila dalam kegiatan ini berlangsung ada salah kata, tindak tanduk, perbuatan yang mungkin mengena di hati, mohon dimaafkan. Mungkin hanya ini sambutan saya mewakili ketua panitia. Wassalamualaikum warahmatullahi wabarakatuh. Selamat sore.
Thank you for the chairman for the very warm welcome. Now, the International Public Lecture of the Permian and Triassic Exotic Blocks of Timor is officially open.
Terima kasih kami ucapkan kepada Ketua Panitia yang telah memberikan kata sambutan. Dengan ini acara kita pada sore hari ini resmi dibuka.
Ladies and gentlemen, now we move to the next agenda. It is the speaker introduction and followed by presentation of the material by the speaker, and after that, followed by a question and answer session.
Hadirin dan hadirat, kita beralih kepada agenda selanjutnya, yakni pengenalan pembicara dan dilanjutkan dengan pemaparan materi yang akan dilanjutkan dengan sesi tanya jawab.
Alright, for Mr. Arep, time is yours.
Okay. First of all, I would like to say again thank you to Hugo for making the time to give a talk to us here. Jadi pertama-tama saya ingin ucapkan terima kasih kepada Prof. Hugo untuk memberikan waktu untuk memberikan kuliah umum ini. So so basically there's going to be 2 sessions. You're going to give your talk and afterwards you will have a Q&A from the audience. Jadi nanti kuliah umumnya awalnya beliau akan kasih kuliah umum. Dan nanti ada tanya jawab untuk sesi berikutnya. So maybe I just give a brief explanation of what the topic is, the talk is gonna be about. Jadi mungkin saya ingin memberikan sedikit gambaran umum ya, menyangkut pembicaraan atau kuliah yang akan diberikan. Jadi nanti beliau akan memperkenalkan dirinya sendiri, tapi beliau ini sudah penelitian keliling dunia untuk melihat tentang fosil-fosil di umur Trias awal. Ya. Jadi mungkin teman-teman dari biologi juga pasti punya materi kuliah untuk tentang paleontologi dan sebagainya. Di tambang juga kita punya materi-materi tentang geologi dan sebagainya. Dan beliau ini sangat tertarik dengan fosil-fosil, ya khususnya amonit. Ya. Jadi beliau punya 2 bidang keahlian spesifiknya. Oke, jadi yang pertama itu untuk morphogenesis, isn't it? Yeah. Morphogenesis. Biological pattern, jadi pola-pola biologis dari fosil-fosil amonit ini. Nah, itu satu spesialis dari beliau. Spesialis kedua adalah menyangkut fosil-fosil amonit yang berada pada umur Trias awal. Jadi pada umur Permian itu terjadi suatu kepunahan besar. Okay? Ada suatu kepunahan besar dan hampir 80-90% daripada hewan-hewan dan semua spesies itu mati, hilang semua. Nah, beliau ini mau meneliti kapan pengembalian development daripada hewan-hewan spesies yang ada itu pada umur Trias awal. Jadi pada saat umur Permian terjadi kepunahan, terus pada awal Trias awal itu mulai berkembang lagi hewan-hewan yang kita bisa teliti di dalam batuan dan fosil-fosil yang ini. Okay, so basically that's a brief introduction on the talk, and yeah, Hugo, I'll give you the stage for this. Okay, dan mari kita sama-sama sambut dengan tepuk tangan untuk Prof. Hugo.
Well, thank you, Adept, for the introduction, and I'd like to thank all the organizers of this for this talk. And I'm quite happy to see that the public is very young, and well, I can only encourage you to attend talks from foreign scientists because it will usually add to your education. Okay, so we're going to talk. I mean, I'll speak on this screen because the air conditioning is quite nearby. Thank you. Can you hear me? Yeah. Okay, so you see the complete title is The Origin, and I insist on this word, the origin of Permian and Triassic exotic, in quotation, blocks in Timor. And I didn't intend to give a lecture on this topic. I had other things in mind when I left Switzerland, but after a little bit more than 2 weeks of field work, we accumulated quite a few new data, and I'd like to show you how important is field work for all earth sciences, and in this case, in particular, for paleontology, for stratigraphy, for mapping, and for structural geology. This is a work done by one of my colleagues and Adept from Nusa Cendana. And this is part of a big project which is funded by the Swiss National Science Foundation, with which I've been working since almost 40 years. All right, next. What direction should I point in? Okay. What are our original goals in this project? You know that during the history of the Earth, there were several so-called mass extinctions, where more than 50% of the species, at least in the marine realm, went extinct in a very short time, geologically speaking. So in our case here, we are dealing with the largest of all mass extinctions, which took place 251 million years ago. That's the Permian-Triassic boundary. And nearly 80 to 90% of the marine species went extinct at that time, in a very short time interval, in the order of magnitude of 100,000 to 200,000 years at most. And on land, there were no extinctions, but complete ecological reorganization of land plants. That means it was not a normal flora on land, but a flora dominated by ferns, indicating stressful conditions. So in the case of what is unusual in the case of the largest mass extinction at the Permian Triassic, in short the PTB, is that it took unusually long for diversity and ecology to recover from this mass extinction. In comparison with other mass extinctions like the Triassic, Jurassic, or the Cretaceous tertiary boundary, it took 5 million years. It took 5 million years in this case for a complete recovery, whereas in the case of other mass extinctions, it took at most 1 million. So something went really, really bad at that time, and that's why we are trying to understand why it took so long in the case of the Permian Triassic mass extinction for the faunas and the floras to recover. What we discovered some 15, 20 years ago is that after the main Permian Triassic boundary mass extinction, we found out that there are subsequent extinctions during the early Triassic. So it was not a single extinction. There was the big one at the PTB 251 million years ago, but it was followed by at least 3 or 4 subsequent extinctions within the next 5 million years. Of course, these subsequent extinctions were not as bad as the main one, but for groups like ammonites, which are marine cephalopods, it was worse than the Permian-Triassic boundary mass extinction. And in this multidisciplinary project, which is called the Synergy project, which is a special class of project from the Swiss NSF, our goal is to understand and model shifts between extreme climates. Sorry, I did these slides in a hurry. I was hoping to do them in we were busy with administration, and there might be some typos. So we want to understand here the shift between extreme climatic changes that occurred during those 5 million years and which likely caused those subsequent extinction. I should add that the main extinction, the big extinction at the PTB was caused by massive volcanism. Within something like less than a million years, you had something like 50 million cubic kilometers of basalts that were erupted in northern Siberia. And this, of course, polluted the atmosphere, polluted the ocean, and led to a biological crisis because of all the chemicals that were injected in the atmosphere and in the ocean. We also want to understand the respective roles of biotic, that means in the sense of ecological, and abiotic, that means physical, chemical, and so on, stresses that were at play during this recovery. And as my backyard here, I am also really interested to reconstruct the evolution of ammonoids during this time lapse, because they underwent massive evolutionary radiations and subsequent quick extinctions. So there were cycles of extinctions and origination during those 5 million years. Why Timor? Now, Timor is well known for yielding the so-called exotic blocks, mostly of Permian age and of Triassic age. And these faunas were collected and first described in the early 20th century by the Dutch geologists and paleontologists. Subsequently, in the 60s and the 80s, the Permian ammonoids were studied mainly by Americans, but because these faunas were found in blocks, in isolated blocks, a couple meters, or the biggest could be 20 meters, but they are extremely rare. Usually the blocks are a few meters, 1 or 2 meters, or a little bit more, but it is difficult to reconstruct a sequence. It is difficult to reconstruct a normal geological stratigraphical succession of the different species if you have only blocks. So that's why the American who worked on on the Permian ammonoid biostratigraphy did it without stratigraphy, which was a catastrophe because they first made guesses about the evolution, what the evolution should have been, and then they positioned the different fauna as a function of their guesses. So it's just the opposite that you should do. You should go to the field, find sections, or rebuild sections by compositing several blocks, and then look at what is the stratigraphy, what is the stratigraphic order with which species do appear and species go extinct. This is the way you should do it. You should not put the cart before the horses. The horses should be first and the cart should come next. In the literature, these rich, highly fossiliferous Permian and Triassic blocks are usually labeled as being exotic. So in the discussion, I will keep this for the discussion, the definition of exotic blocks, but it means that these blocks were detached, active, were redeposited into a basin, where they were redeposited in deeper water into the basins, and they form breccias. They're from accumulation of fragments which were caused by active faulting, usually normal faulting during the rifting phase, when a new ocean is being born, when a new ocean is appearing, you will have stretching of the lithospheric crust, you will have normal faulting, you will have extensions, and this will generate lots of breccia. And after these breccia, these units, these sedimentary units, will be remobilized during the collision, during the compression, and they usually end up as tectonic napes that are rocks that have far traveled from their original, from their genuine position of and depositional site. So this is the concept of exotic block. And this concept has been applied to both the Permian Mobisi Formation and the Triassic red Hauenstein facies or Ammonitico Rosso. I'll use the Hauenstein facies because that's the way we name it in Europe. It's the same thing than the red Ammonitico Rosso. And since about 2000, conodonts, which are microfossils, which are assigned to a very primitive group of vertebrates that disappeared at the end of the Triassic. You can find teeth which are half or a fourth of a millimeter. When you dissolve the limestone, you can find those teeth, and this is another group which had, like ammonites, which had a very high evolutionary rates. So that means ammonites and conodonts, both groups had a very high evolutionary rates, and are usually useful if you want to get precise age, if you want to date your rocks in a precise way. But the problem is that most of the conodont workers are using wrong methods, and the block problem, that means the absence of comprehensive stratigraphic successions and data only available from block, also strongly make it extremely difficult to reconstruct. Well, it's working. Okay, just a brief picture to show you this research group called Synergia. And in this group, combination of several scientific fields. It's a multidisciplinary group. Of course, we have paleontology, stratigraphy, plate tectonics, stable isotopes, radiogenic isotopes, when we want to date, for instance, zircons from ash layer. And we have physicists doing climate models with the help of supercomputers. Here is a brief graphical summary of what we do. The horizontal axis here is time. You have here the numerical ages, which we obtain ourselves from volcanic ashes interlayered with fossiliferous beds. So you can see the total here is about 5 million years. Here we have the Permian Triassic boundary, and here we have the early Middle Triassic boundary. Now, there is a curve here showing some cycles. This curve here represents carbon isotopes from open ocean and seawater. These carbon isotopes are used as a kind of proxy for the atmospheric pressure of carbon dioxide. So it shows you that in the late Permian, you had very positive values of these carbon isotopes. Here at the Permian Triassic boundary, you have a huge negative shift, and then the whole isotopic system of the world ocean underwent 3 big consecutive negative shifts, interrupted by 3 positive by 3 positive shifts of the carbon cycle. And what is also interesting is that on average, the late Permian was between +5 and +4. And after that, the new equilibrium that was reached in the middle Triassic was around +3. So you had a change of the base level of the PCO2 in the atmosphere, and also with the equilibrium between atmosphere and ocean. So this is what is intriguing. What generates those cycles in the carbon cycle? And here you have a color code. You have a color code which highlights the main big changes we observe at the global scale during this time interval. For instance, extinction of ammonites and conodonts, which is here coded as pink. So you see at the Smithian-Spathian boundary here, at this boundary here, during this positive shift, there is a big extinction, and the ammonites almost died out completely at this time. And there was another one here at the end of the early Triassic, just before the middle Triassic. And it also occurred during a positive shift of the carbon. Now, the opposite, the diversification of ammonites and conodonts, coded here in green. You see that the green phases are always with are close or nearly almost at the positive shifts. That means when you had cooler climate. The negative phases here represents warm or hot climate, and the positive shifts here we interpret as cold climates, and even perhaps at the climax of the positive shifts with short ice ages. Why do we suspect that we had short ice ages during this globally warm or hot early Triassic? Because of the change of sea level. The only way you can massively change the position of the sea level is by storing water on continents, either under the form of glaciers or under the form of permafrost. If you build sea ice, because of Archimedes' force, the sea level will not change. In order to change the sea level, you have to subtract water from the ocean and store it on the continents. In orange, yellow here, you see these bars, which are always during the maximum negative shifts here. For this one, this still needs to be confirmed. There is a question mark. What do we have here during the peak hot climate? On land, we see that terrestrial plants were dominated by ferns. And again, ferns are the plants that will be the most resistant to abiotic changes. That means extremely high temperature, perhaps acidic conditions. These ferns represents the main group of plants that are the most resistant to chemical changes on the surface of the continents. So you see, we keep having the same pattern that is repeating. During a complete cycle, we have a succession of different colors whose explanation is given here. And these changes are perfectly in pace with the carbon cycle, with the changes we see in the carbon cycle. So if here we know that there was massive volcanism at the Permian-Triassic boundary, subsequently to that, there is no clear evidence of additional volcanism that could have changed, that could have triggered these changes in the carbon cycle. So we have to think about other potential mechanisms than volcanism. Volcanism played a role here, but not during the next 5 million years, contrary to the common belief, and contrary to what I thought during the first 15 years of this research. Very quickly, The geologist will certainly know about this, but the biologist perhaps not. Here you have the stratigraphic chart, and the Permian is represented here in red, and the Triassic in deep purple here. And you see that the boundary here is at 251. The base of the Permian is at roughly 300 million years. The Permian-Triassic boundary at 251, and the end of the Triassic at 100. That gives you an idea about these ages for those who are not familiar with stratigraphy. Now, after having looked at it in time, we'll look at it in space. If the slide wants to come back, I don't know in what direction I should point the pointer. No, it's... Okay. Here, this is what the world looked like 251 million years ago. And you have a single continent called Pangaea, which is subdivided in two parts because of this ocean here. You have this ocean is called the Tethys, and the northern part here is called the Paleotethys, which is more ancient than this part here, which is called the Neotethys. And where was Timor at that time? All the rocks, all the Permian and Triassic rocks we can find in Timor were somewhere here along the northern margin of Australia. Except the alloctonous, the really alloctonous rocks called the Mutis, which are mainly abundant in the northern part of Timor. All the other Triassic and Permian rocks were situated somewhere here along the northern margin of the Gondwana continent, more specifically north of Australia. But you see that the oceans, if I can go back, yeah, oops. You see that the oceans were not empty, and you already had many blocks in the ocean, in the Pacific, in the Eastern Pacific, in the Western Pacific. You had many blocks here already corresponding to highly active tectonic zones. And this must be really subdivided in two parts. The old Tethys, which is in the northern part, like this, and the new Tethys, which is here in the southern part. So that you have an idea where those Permian and Triassic rocks from Timor were derived from. What are our objectives in Timor? The first one, to reconstruct the early Triassic ammonoid biostratigraphic sequence. Nobody did it so far. So this is a work we've been doing for quite a long time all around the world, because we need to have a good time and space distribution of all these species during those 5 million years. There were drastic biogeographic changes linked to those climatic changes, and we need to track that with the marine faunas, and specifically with ammonites and conodonts. We also want to test for an increased longitudinal gradient after the main extinction at the Smithsonian-Spathian boundary, which occurred in the early Triassic. After roughly the first third of the early Triassic, there was one of the middle cycle, the one which has the biggest carbon change, the biggest carbon isotopic change, also induced a change in the distribution of the ammonites. Before, the ammonites, you could follow the same fauna at the same latitude all around the world. In pre-Spathian time, before this boundary, all of the faunas were controlled by latitude. And you could find the same fauna in the equator whatever the position around the globe, the same fauna in the boreal realm, whatever the position, whatever the location in the northern continents. But after this, there was a subsequent change, and this latitudinal distribution was broken, and each area developed a peculiar fauna, a specific fauna, which was different from other faunas at the same latitude. So there was really a change in the distribution of in the type of distribution of the species. We need also further validation points for the evolution of the sea surface temperature. SFT is the abbreviation for sea surface temperature in time and space. And these we measure from those conodont teeth by measuring oxygen isotopes from their teeth. So they are microscopic teeth, and from these we can measure the oxygen isotopic composition, which is a proxy for sea surface temperature. We also want to improve our understanding of the Hallstatt facies deposition during the early Triassic. I mean, those red limestone, you will find them in the early, in the middle, in the late Triassic, but these red limestone are usually interpreted as offshore hemipelagic deposits without any siliciclastic, without any sand, without any mud in this rock. It's pure limestone. So this you will not find close to the continent, but you will find this far away offshore from the continent. We also want to reconstruct the paleogeography. This is something extremely important. And the last question, which is now more than 100 years, this question which is unsolved since more than 100 years, is how these blocks, the so-called exotics, are generated. Why we don't find a complete outcrop with a succession of all the different ages indicated by the ammonites and conodonts, but we find only blocks? There must be a mechanism in order to explain how these blocks were generated. And this has been a puzzling question for more than a century. So I'd like first I should say that I am a relatively newcomer in Timor geology. I've been only 2 times in Timor. The first time was in 2019. It was in Timor-Leste and in the area of Manatuto. And in this area, a colleague from Timor Gap, from the oil company of Timor-Leste, first found at Mount Lilu, which is this massive. It's here you see only part of it, only one side. It's a big limestone massif, which is at least, in its largest dimension, which is at least 2 kilometers. So it's not a small block, it's a huge block, and it's even more than a block, because these limestone of Permian and Triassic age are thrusted, they're resting upon siliciclastic rocks of Jurassic and Cretaceous age. So it's not normal to find old rocks on top of young rocks. Normally, the old rocks should be below, and the younger rocks should be above. Here we find the opposite. So that means that somewhere here, there is a big thrust, there is a big low-angle thrust that allows the juxtaposition, the vertical juxtaposition of those Permian and Triassic rocks on top of younger rocks. And it was Isaias, there is a typo, the name is Isaias Santos Barros. He's the one who first noticed that on the north, that there were ammonites, that there were Triassic ammonites on the northeastern side. So that's why we went there with him. And within the whole massif, we realized that the stratigraphy, the internal stratigraphy, was fairly consistent and coherent with the Permian Mobesi limestone and the early Triassic, and the Triassic red limestone, followed by Middle Triassic massive gray limestones containing chert nodules. So that means that within this huge mass of 2 kilometers, stratigraphy is very coherent, very continuous, although there are small faults, but you can restore the small faults, it's not a problem. And the whole thing, the whole set of Permian and Triassic rocks here is resting on top of younger rocks by means of a thrust fault. So in tectonics, in structural geology, you would name that a tectonic scale. A tectonic scale is something that has a size of several hundred meters to several kilometers. So it's much bigger than the comparatively small blocks we find in West Timor. What is also interesting in Mount Lilu, in the Manatuto area, here you have an outcrop, here you have one of my PhD students, and this is the outcrop that was first discovered by Isaias, and here we realized that the first bed, you see the massive bed here, is Permian, and the thin bedded limestone which is resting on top of it is early Triassic. But the beginning of the early Triassic is missing. The very first bed, which is here, is already Smithian in age. That means that the two first stages of the early Triassic are missing. That means here there is a big stratigraphic gap. Sedimentation is not continuous. You have big hiatuses, in particular, and especially here, the Permian Triassic boundary. So this we could confirm by means of 3 sections in the massif showing the same succession of rocks, probably middle Permian. There is no indication that the late Permian is preserved, and we've got already something which is more or less in the middle of the early Triassic, which is directly on top of it. That means during this, all the time that is missing here, that means that either the sediments were not deposited or they have been subsequently eroded. There is a big gap, a big hiatus, and this is very important to understand why. Wow, it's getting too fast at one time. Okay, so you see, here is, that was also the first time a complete stratigraphic succession of the early Triassic and the middle Triassic could be reconstructed in Timor as a whole, both east and west. And here you've got the top of the Permian, which is represented by middle Permian, and here you have all these red limestone. Here you have a scale, the vertical scale here is in meters, so you see that it's not a very thick sequence, but this is the first time that we could reconstruct, that we could access a complete early and middle Triassic succession. And already in the field, just by collecting, by breaking each bed and looking at the ammonites, we figured out that a lot of time was missing here in this succession. That means, with respect to other places in the world where you have continuous sedimentation, here sedimentation is highly discontinuous, and the whole succession here is pervaded with gaps, some of them being of more than 1 million years in duration. So that means that the record here in East Timor is extremely discontinuous and has a lot of gaps in it. Here you can see, just from one bed, an assemblage of monoid which was extracted from one bed, and this association contains characteristic fossils over a very short time interval, plus new species and new genera which are typical of this area, which are not known elsewhere. So, what did we do the last 2 or 3 weeks together with my colleague, with Adept? We went to this area, which is east of Niki Niki, and the river here is called Noil Bunu, and we looked at all the exposures along this river here. Where we worked, the places where we worked are highlighted in red, and you have a scale here showing the distance on the ground. This is 2 kilometers. Here you have the village of Besleo, here you have Oileon. And of course the north is towards the top. So we, except for Noil Tobe, which was first described by the Dutch geologist and paleontologist, and the northern part of Noil Bunu, all the rest here has never been explored for Permian and Triassic, and so that's what we did, and we had quite a few surprises. Yeah, that shows you, I mean, it's a lot of work if you want to do precise work in the field, so you have to take time, and this represents between 2 and 3 weeks of field work. So, to our big surprise, what we found out is that these exotic blocks, which can vary from 50 centimeters to 10 meters, or even more sometimes, but the bigger blocks are very rare. They are not distributed at random. If you map the area, if you do geological mapping, you will realize that these blocks are concentrated along 2 lines in this area. The line here parallel to Noil Tobe, and another line here, which I call which goes through Oileon village. And all along this white line here, along these 2 white lines, that's where you will find blocks that have not been transported by the big rivers during the flood. Of course, these blocks can be transported several hundred meters from their original location, but you will trace back the place where they first pop up at the surface. And these places are along structural lines here, which in fact corresponds to big reverse faults. So these blocks, the Permian and the Triassic, which normally is way deep underneath, several kilometers, fragments of these rocks, of those Permian and Triassic rocks, were pushed to the surface along these big thrusts here. And what is a thrust? That means the rocks, you see the small tooth, so the small tooth are pointing toward the plate which is over, and this part is the plate which is underneath. So what does this mean? If I draw it on the blackboard, for those who are not familiar with thrust faults, if at the beginning you have a sequence of layers like this, a thrust fault along the dashed line here, what will be the result of this? It will be a displacement whose essential component is horizontal. And that means that this is the upper plate and this is the lower plate here. So this is what these thrust faults are. They are low-angle reverse faults. So that means that this part has been pushed up and did climb on top of the lower part here, but the rocks here are exactly the same than here. And the formation, the edges are the same, but they are repeated because of this reverse fault. So this is completely new, and nobody realized, because nobody did detailed mapping, that these blocks are not distributed at random but really are aligned along thrust faults. And this largely explains how blocks that would be rocks that are somewhere here can be transported up until they reach the surface. Here on this diagram, I tried to summarize all these observations and to test for internal coherency. So here again, the red line here indicates a thrust fault. So you see basalt in green, in dark green, that's the Mobesi basalt. In orange, yellow, that's the Mobesi limestone. In pink color, the pink color represents Triassic red limestone. The blue color represents Jurassic sediments. And on top of this, what do you have? You have completely squashed Cretaceous deep water rocks, thin-bedded radiolarian-bearing rocks on both sides of the thrust. And what is really peculiar to these thrusts is that the Bobonaro Formation, which are pure shales, highly ductile rocks, are always involved into these thrusts. So the black rocks here, which are heavily folded and squashed, these are Miocene in age. The green squashed folded rocks are Cretaceous. Blue is Jurassic, Triassic. The yellow is Permian, and the basalts at the base are Permian. So these basalts here record the opening of the New Tethys, the southern part of the Tethys, and you will find them everywhere in mountain ranges where the new mid-oceanic ridges did appear. For instance, you will find them in Oman, you will find them in the Himalayas, and so on, in Kashmir, and they have exactly the same age, the same chemistry. And now, what about our blocks? So you see, what do we find along these thrust faults? What kind of blocks do we find? The large majority of blocks we find are Permian, derived from the Mobesi. A minority of blocks are Triassic, the red limestone. A small number, but usually big, are made of basalts coming from the base. The Bobonaro shaly clay, represented here in black, must have facilitated the push of these blocks upward. And these blocks represent, in fact, broken Gondwanian, sorry, there is a typo, there is only one N, broken Gondwanian basement in quotation. So these rocks here are very hard. The Permian and the Triassic are usually massive limestone and basalts. So these rocks will not be deformed easily. They will break, whereas the shaly rocks here will be squashed. They are highly ductile and they will be easily compressed or stretched. So this represents, for both for the Noil-Tobé thrust and for the Oileon thrust, this represents the summary of the geometric relationships between all these rocks and the blocks. And this is what holds the key to our question: how did this block form? How did this block originate? So the first mechanism that is needed, and which is documented from the field, are those thrust faults. But we noticed something contradictory. Here, that's the base of that's a Cretaceous limestone, and when you see this kind of structure, which technically we call a boudin, you see this was a white limestone bed with a limestone bed, and you can see here with a hammer for scale, you can see how this bed has been broken into slices, just like a sausage which is cut with a knife. And the whole thing has rotated and has been stretched. So if you see something in the field, what does this mean? That means that the upper part moved from the left to the right, and that the lower part moved from the right to the left. So this is stretching, this is extension. This is extension. So how can extension occur together with compression? For a thrust fault, you need compression. And then what is really weird is to observe in the same rocks involved in this thrust fault to observe stretching. Stretching is extension. At one time you have, on one hand you have compression to make the thrust fault, and on the other hand you have extension. This is not compatible. It's more than a simple thrust fault. There must be something else. If it was a pure thrust fault, you would not see such stretching structures. It would be tilted the other way, and the small slice would climb on top of each others if it was compression. So here it's extension, stretching. Now, here you have a field picture. You have here a sledgehammer for scale. So this block is about 4 to 5 meters thick stratigraphically. This one is 3.5 to 4 meters. You can see the black spots here. The black spot that you can see here where on the rock, where we broke the rock, these are ammonites coated with manganese oxide and iron oxide, which is typical from the deep ocean, indicating that the manganese came from the submarine volcanoes, like the mid-oceanic ridge. You can see the red color. When on a fresh cut like this, you can see the red color. If it's weathered, it looks gray. But what is really striking is that you see that most of the blocks, on all of their size, they are coated with a breccia. You see all these blocks, the small blocks, which are just coating the big block. And the small blocks, they come from the big block. It's the surface of the big block which is broken into small pieces. So this indicates that this block has been sheared during the transport along the thrust plane. This block has been partly grinded. And at the end, you would have only sand. But hopefully, we have still big blocks of Permian and Triassic. So all of it has not been destroyed. Now, here is a close view of those red limestone. You can see the bedding, which is here horizontal. You have here 20 centimeters for scale. And you see that all the white spots, they are calcite filling of the ammonite chambers. So you can see that it's very rich. It's not condensed. That means that each of these beds represents a certain amount of time without big gap in between the beds. And this we infer from the fossils they contain, from the species which are contained here in those different beds. We've also found 2 blocks that contain the Permian-Triassic boundary. Here you see you have a small block which was nicely exposed in the riverbed. The other one is a big block, but which is in the trees above the riverbed, so we had no light, so that's why we had no sun, so that's why I preferred to illustrate the Permian-Triassic boundary with this picture. You see, most of the block here is made of white limestone. And this white limestone here contains middle Permian brachiopods. And on the top of it, you see you have red beds here. So now if we look closer at these red beds, we see Smithian ammonites, early Smithian ammonites. Here you have a scale, a centimeter scale, showing you that this is already a big ammonite. And together with these red limestone and fossils and ammonites, representing again the Smithian, we found breccias with elements derived from the Permian basalt. So that means that at this time, active faulting was already active, and that some of the basalts, which are at the bottom of the sequence, were pushed up and eroded along the faults and redeposited here into offshore marine basins during the Triassic. But what is also very interesting here is that exactly like the Manatuto section, the Mount Dilu section, the beginning of the Triassic is missing, and the end of the Permian is missing. So that means that right here, we have a lot of time which is missing, several million years. And Vanner, in the 30s, already published the occurrence, already reported about 4 blocks containing the Permian-Triassic boundary, but where the top Permian was missing and the base Triassic was missing. So now we've got one more PTB block, a big tectonic scale in Manatuto, and we've got 2 additional blocks here east of Niki Niki showing exactly the same. So it seems legitimate to infer that the base of the Triassic will be missing everywhere in the offshore sequence of red limestone, and that the top of the Permian underneath is also missing. So this is a gap which is extremely widespread and which might cover the entire island of Timor. So this has a strong meaning for paleogeography and for sedimentary processes and sea level changes and tectonic processes. We also did find some very rare blocks. Unfortunately, one of them I couldn't take a picture because the battery of my camera was dead, so I can only illustrate one. You see, this is a breccia. You have the hammer for scale, which contains angular fragments of radiolarian cherts, of purplish radiolarian cherts. But these look completely different than those from the Cretaceous. They have a completely different aspect than those of the Cretaceous. And my guess, it's just a guess, but we took samples, and these samples will be analyzed for the radiolarians. My guess is that these fragments here could well be Triassic. In this case, this would mean that next to the red limestone that contains ammonite, we could have trough that contains water sediments, like radiolarian cherts. And the other rare blocks we found 2 blocks, only 2 among several hundreds. I don't know, we've seen maybe 500, 600, 700 blocks. Only 2 blocks were made of amphibolite. So amphibolite is a highly metamorphic rock, and it cannot come from any of the formation we discussed so far. It cannot come from any rock of Gondwanian origin similar to those we discussed so far. This means that probably these blocks originate from the Mutis complex, and the Mutis is the top structural unit which mainly crops out in northern Timor, both in the east and the west, and which do not belong to Gondwana, but belong to the Banda terrain. And this, finding a block like this among the other blocks along this thrust fold has huge tectonic implications. That means most of the tectonic model so far cannot explain this. That means that the Mutis must have arrived as far south as Niki Niki. And one way or another, these blocks were involved in the thrusting. That means that the transportation from the Mutis from the north to the south predates the thrusting. Otherwise, you would not find these rocks along the thrust faults we discovered in the field. Just to wrap it up, some preliminary conclusion. Of course, there is all the lab work that will come behind this. The permanent Triassic so-called exotics are not exotics. They are simply broken pieces of the Gondwanian basement, which is underneath the whole sedimentary sequence. They are absolutely not exotics. They are not far traveled. They've just been pushed up to the surface thanks to the thrust faults, and probably, this is something I forgot, the stretching. How can we explain the stretching? For this, I should go back to the geometric relationships, if I can go back. Oh, okay, it's written here. So the fact that you have stretching contradicts the mechanics of thrust faults. The only way you can generate this stretching is by means of shale diaparism. The Jurassic is very shaly, and then the Bobonaro is just shales, just like soap. It behaves just like soap, and this means that along the thrust fault, you see, if here you have a big piece of soap, like the Bobonaro, this soap is very ductile and will be extruded along the thrust fault. It's just like a lubricant. And if you have this, then you can explain extension like this. You see, this is what we observed, the structure we observed at a smaller scale. If you are pushing up the rocks from underneath, and of course this will help the blocks that are already broken here, this will help the blocks to rise to the surface. But injecting soap in a fault like this will bring our rocks from here very quickly to the surface. So they are not exotics. They are simply brecciated parts of a thrust fault whose movement towards the surface was facilitated by soapy rocks like the Bobonaro Formation. How can I get back? Please, can you activate the pointer? Okay, I'd like to thank you for your attention. I hope I was not too long. Thank you very much.
Okay, right, thank you, Hugo, for the very interesting talk. Yeah, we did find some interesting stuff in the field, so maybe I would try to summarize a bit in Indonesian for some of the students here. Jadi, ya, sedikit summary menyangkut kuliah umum yang disampaikan oleh Prof. Hugo. Lebih menyangkut bagaimana hasil observasi atau penelitian yang dilakukan selama beberapa hari atau beberapa minggu yang lalu ini. Jadi seperti tadi beliau sampaikan bagaimana beliau ini coba untuk melakukan penelitian dalam early Trias atau awal Trias dan pada saat terjadinya mass extinction atau kepunahan besar itu pada saat akhir daripada Permian itu akibat dari ada suatu massive volcano atau gunung api yang besar di daerah Siberia. Nah, dan blocks yang tadi disebutkan di sini ya, yang umurnya awal Trias ya, itu disebutkan sebagai yang sama juga kita bisa dapatkan fasiesnya, litologinya itu disebut sebagai Hallstatt fasces. Nah itu didapatkan di daerah-daerah Austria. Dan beliau sudah melakukan penelitian juga di Timor Leste. Di situ beliau menunjukkan Gunung Lilu itu sekitar lebih daripada 2 kilometer. Ya. Dan bagaimana gunung batu besar ya, sebesar itu dia bisa berada di atas permukaan. Sedangkan umurnya lebih tua dibandingkan batuan-batuan yang ada di bawahnya, yaitu umur Cretaceous dan umur Jurassic. Okay. Dan yang menarik juga adalah pada saat Permian dan Trias itu ada beberapa juta tahun itu batuannya tidak ada di timur. Okay. Jadi batuannya tidak ada di timur, ada istilahnya hiatus. Ya. Jadi entah batuannya memang sama sekali tidak tersedimentasikan atau memang batuannya ada tetapi tererosi dengan cepat. Okay. Jadi ada pada boundary atau batas antara Permian dan Trias itu. Okay. Thank you Hugo. So the next section would be Q&A. Nanti saya minta tolong jikalau ada dari bagian Zoom atau YouTube yang online, jikalau ada pertanyaan, tolong nanti disampaikan. Tetapi mungkin yang dari audiens di sini, di ruangan ini mungkin ada yang ingin ditanyakan menyangkut topik kuliah umum yang disampaikan pada hari ini. Saya persilahkan.
And don't be afraid to ask a question. There is no stupid question.
Jadi ya jangan takut untuk menyampaikan pertanyaan karena tidak ada istilah pertanyaan yang bodoh gitu. Ya, jadi silahkan bertanya.
Baik, jadi ada satu pertanyaan dari peserta kita yang secara online. Pertanyaannya, bagaimana pengaruh struktur geologi terhadap petroleum sistem dan mood volcano di Pulau Timor?
Okay, Hugo, so there is one question from the audience online via Zoom. They were asking the structures that you explain, what you observe in the field. Okay, how can you correlate it with the petroleum system and also the mud volcanoes occurring in Timor?
Well, in the area we studied, there are absolutely no mud volcanoes. That's the first point. I mean, mud volcanoes would be fairly obvious on Google Earth. I mean, the western end of West Timor, there are many mud volcanoes, and these you can spot immediately on a Google Earth view. So here, we didn't notice any from the satellite images, and in the field, we didn't see any. But one of the conclusions here is that shale diapirism, how to say, you cannot explain the association of compressive thrust faults with extension, with stretching, without having mud diapirism at the same time, without having the Bobonaro acting as a smear of soap along the thrust fault. How does this relate to oil reservoirs? Will completely depend. I mean, for an oil reservoir, you need two things. are three things. Making oil is just like baking potatoes, but the potatoes is organic matter. So first you need organic matter, and this organic matter must be cooked at a certain, with different combinations of time and temperature. What matters here is not the temperature alone. What matters here is not time, how much time alone. What matters is time multiplied by temperature. That's the quantity of heat. This is what will yield the maturation of the organic matter. So you can have a low temperature during a very long time, or a high temperature during a very short time. The result will be the same. It's not a question of temperature, it's not a question of time, but it's a question of temperature multiplied by time. It's just like a pressure cooker when baking potatoes. It's exactly the same. The two other things you need is a source rock. What is a source rock? It's a rock that contains a lot of organic matter. Usually, I mean, for instance, in the Middle East, most of the oil comes from the Cretaceous, but at that time, you had planktonic foraminifera, you had a lot of plankton in the ocean. And most of this organic matter is derived from the plankton for the Cretaceous and the Tertiary. You had no plankton. Apart from one group called the Acritarchs, you had no plankton until the late Triassic. The first nanofossils, the first coccolith, the first true plankton first appeared at the end of the Triassic. So that means that usually pre-late Triassic organic matter is frequently of terrestrial origin. And that means that this organic matter is transported from the continent into the ocean via the rivers and the delta. Just look at the flood in Olden Oil. I mean, when you have a flood in an oil and you carefully look at this, it's full of plant debris. It's full of debris from the soil. So this organic matter will end up in a delta, and then in the next trough adjacent to the delta. And the last thing you need is a reservoir rock. A rock where when the oil has become mature, it will migrate upward and it will be trapped into a porous rock. So the porous rock could be a poorly cemented sandstone, or it could be a heavily fractured limestone. But most frequently, and on top of it, you need a sealing rock, just like an oil-proof roof on top of it. Otherwise, the oil will continue to rise up. So ideally, you would have a sandstone, a body of sandstone, capped by shales, which will make it impermeable, and in order to trap the oil, the droplets of oils which are migrating upwards. Any thrust, potentially any thrust, I mean, if either you must have anticlines, a simple anticline could act as a trap, for oil. Thrust faults could also act as a trap, provided somewhere you have an oil-proof roof preventing the oil from reaching the surface. And for instance, in East Timor, I saw many seepages, methane seepages. So that means that the hydrocarbons are reaching the surface and they are burning in the middle of nowhere. So you see, it's a question of luck. Of course, the presence of thrust faults will increase the chance of finding a reservoir. But if we go back to our stratigraphic succession, can you put the slide back?
Which slide?
Yeah. Thank you.
Terus.
Okay, if we look at this here, where is the first rock rich in organic matter? In this succession. Here we have basalts. Here we have high energy shallow water limestone. Here we have relatively high energy hemipelagic limestone offshore. And you saw those blocks. Those blocks do not contain any shales. They are not fractured. They are not porous. And they are extremely hard to break even with a sledgehammer in the field. You can ask Adept for that. So the first group of rock that may potentially contain organic matter, but not as much as the Bobonaro, is the Jurassic, represented in blue here. So that means, for instance, if the thrust planes, instead of being 45 degrees like this, is at low angle, you will increase the potential for oil derived from the Jurassic or from the Cretaceous or even from the Bobonaro to be trapped by the thrust plate of this fault, by the upper plate of a reverse fault. I hope this answers the question. But I must say that I am not an oil geologist.
Teammates. Okay. Yeah. So maybe I'll translate a bit because the question was in Indonesian. So jadi mungkin karena pertanyaan tadi di dalam bahasa Indonesia, coba saya translate sedikit menyangkut penjelasannya. Jadi relasi daripada temuan ini terhadap mud volcano atau semburan lumpur, sama seperti kalau ada yang di sini dari daerah-daerah Atambua atau di daerah-daerah di Malaka dan sebagainya, kalian lihat misalnya di daerah Masin Lulik itu banyak sekali semburan-semburan lumpur dan sebagainya. Nah, bagaimana korelasinya terhadap model struktur geologi yang disampaikan tadi, sempat dijelaskan bahwa hasil observasi di lapangan itu terjadi thrusting, jadi ada reverse fault atau sesar naik, ya. Jadi batuan yang lebih di bawah ini dia tersesarkan naik, dan pada area sesarnya itu adalah tempat di mana mud volcano atau lumpur ini adalah media di mana lumpur ini bisa naik sehingga naik ke permukaan, ya. Jadi ini walaupun demikian kita tidak temukan mud volcano atau semburan lumpur di daerah-daerah Niki-Niki dan sebagainya, tetapi semburan lumpur itu sangat-sangat banyak sekali di daerah timur, ya, dan biasanya kita lihat pada daerah-daerah patahan, gitu. Dan relasinya juga terhadap petroleum system. Jadi ya untuk potensi migas lah, minyak dan gas bumi itu bagaimana. Nah, kita kalau lihat dari stratigrafi yang sudah disampaikan, ya, dinyatakan itu yang karena harus dibutuhkan source rock atau dibutuhkan source rock reservoir dengan seal. Dan memang source rock yang tepat adalah pada zaman Jurassic, jadi di atas daripada, lebih muda daripada batuan-batuan Trias maupun Permian, ya. Oke.
Baik, selanjutnya ada pertanyaan dari via Zoom. Mohon bantuan penjelasan dari Profesor tentang paleobatimetri Timor berturut-turut di saat Permian, Triassic, Jurassic, dan Miocene.
So there's a question again from the Zoom audience about, well, can you tell us a bit of something about the paleobathymetry of Timor during Permian to the Triassic, Jurassic, and onto the Miocene or Cenozoic?
For the Permian and the Triassic, yes. For the rest, no, because I didn't study it. So if you don't know, you have to say, sorry, I don't know. but for the Permian and the Triassic, so maybe I thought about this. I will try to use the blackboard to illustrate the image that comes out of this fieldwork in terms of paleogeography. So the Permian, and remember that the basalts, the pillow lavas, and there are beautiful pillow lavas even preserved in those exotic blocks, which are not exotic, but and I saw them both in Timor-Leste and now in West Timor. So the very first basalts during the birth of a new ocean, they do not need to be very deep water. You know, at the beginning, you have a lithospheric plate like this. And this plate will start breaking with normal faults, which we call big listric faults, which we can simplify graphically like this. And what causes the presence of those tilted blocks bounded by listric faults is extension. So you have to stretch your block in order to open a new ocean. There are many places on the surface of the Earth which didn't go beyond this stage, even in Europe, where the rifting stopped in a very early stage. If you take the next, these faults, if I represent the base of the plate, the base of the plate will be thinner and thinner as extension proceeds, as stretching proceeds. And you will have the rise here of basalts, which have a typical geochemical signature, which we call MORBS, M-O-R-B-S, which means mid-oceanic ridge basalts. They have a typical geochemical signature, and these we are able to recognize. So what will be the next stage? The next stage will be the basalts will arrive to the surface. I represent them here in black. And our listric fault will be like this. And our tilted blocks will be, I should do one in the other direction, like this. Okay? So the basalts will be coming up first along these faults here. And it is not, initially, a long time ago, geologists first thought that it was a thermal anomaly somewhere here deep in the mantle, that there was a thermal anomaly in the mantle that was pushing the basalts upwards. Now, structural geologists and geochemists think differently. They think that the cause of this stretching is plate tectonics itself and not what is present underneath in the mantle. So you can have different interpretations with or without a thermal anomaly. Thermal anomaly in the mantle was something fashionable several tens of years ago. Now, stretching of the plates is mostly interpreted in a different way, mostly by the interplay of the different tectonic plates that are pushing or pulling each other's. And at the end, as you keep adding basalt, once the basalt made their way to the surface, here, sea level may not be that deep. You see, sea level may be something somewhere here. Okay? And the first rocks that will be deposited on those basalts are pelagic limestone, open ocean carbonates, open ocean limestone. So the first rocks you will find on top of these will be limestone. And here you will also have deposition. You will also have deposition of limestone. For instance, the Mobesi formation would be something typical in this context. For the Triassic red ammonite limestone, you need more oceanization. You need more basalts. That means you are continuing to stretch the whole system like this. And at the end, the basalts, at the end, what will happen, not at the end, but later in the development of an ocean, what will happen is you will have lots of basalts, lots of basaltic seafloor, uh, 1,000 kilometers plus. And you see, because all the basalts didn't reach the surface at the same point, what will happen with these blocks? What will happen with those big tilted blocks? I mean, the size order of these blocks here is 100 kilometers plus. They are really big blocks. And that means your carbonate shelf is breaking apart progressively because of those tilted blocks. Initially, you had something undisturbed with no faults, a huge carbonate shallow water platform, and this is progressively being broken into pieces because of the stretching and the listric fault. So if you follow now, if we follow, for instance, this block here, which is in the middle of the basalt, and we look at it 10, 20 million years later, this block will be somewhere lost in the ocean. This is the same block in the middle of a basalt sea, in the middle of the ocean. And could be submarine, of course. Because now that you have a true ocean, sea level is much higher. And maybe some of you heard about the carbonate compensation depth. When a carbonate particle settles through the water column, there is a given depth at which carbonate will be dissolved. And the only sediment that will reach the bottom of the deep ocean are siliceous debris from radiolarians. Radiolarians are unicellularians building their microfossils, and they built their skeleton is quite common in the geological record in the deep water ocean because they will resist the dissolution which will affect the carbonate. Carbonate will be dissolved, but opale, which is a form of silicium oxide, will settle down, and here what you will have are radiolarian cherts, thin-bedded, extremely ductile during the compression. And the margins here will be very far away. So that means that the continent will be here. The continent will be in this direction. That means this place here will be here to the right, and this place here will be way far to the left. So the ocean is opening. What may happen subsequently? I mean, some of the oceans can be very old. If you look at the age of the seafloor, today, on today's Earth, there is no Triassic seafloor preserved. The oldest, for instance, in the Atlantic Ocean, the oldest seafloor is of Jurassic, if I remember right, it's of Jurassic age. I may be wrong, it's old knowledge, I'm not certain that it's correct. But for instance, generally, there is no, in today's ocean, there is no preserved Triassic or older seafloor. The only place where you can find the seafloor are in collision zones. These old seafloors, you can only find scraps, bits and scraps of them as names, as tectonic names involved in collisions, in convergence zone. So what may happen after? So the ocean will broaden, and suddenly the direction will change, and instead of having extension, you will have compression. So what happens now if you compress the whole system? You must have a place where the whole system will break. You will have a big fault, what we call a subduction zone, where the convergence will promote the downward underthrusting of part of the system. So that means it could start. Let's imagine we take now this edge of the continent, which is something really massive, really resistant. And we now push from the left side and see what happens. So you will have here the old margin with your, this is the old margin, which was here, and here, the ocean seafloor is being subducted under the edge of the continent. At a given depth, at a certain depth here, it will start melting. This plate, which is heavy, basalts are quite heavy. This plate is plunging, and at a certain depth, if there is water, and water will promote the melting of this plate, so if you start having melting here, you will form magmas, and these magmas will end up here in volcanoes. For instance, Japan is something like this. For instance, the North American and the South American Cordillera, it's something like this. In the Alps, in Europe, we had this also, but long time ago, not anymore. And what happens here in this big fault, called the subduction zone, is that all the sediments which were deposited on the seafloor, oceanic sediments, blocks inherited from the rifting phase. Let's put our small block here. When the whole system is pushed here, these rocks are light. This one is heavy. They will have a different behavior. And here, you know, it's not bigger than a mailbox slit. So you cannot push everything down. There will be bits and pieces of oceanic sediment that will be stuck on top of the subduction zone. This is what we call an accretionary prism. And you see that our little block, on which some red limestone ammonite was deposited, or the Mobisi formation was deposited, is now stuck into a series of slices on top of a subduction zone. Now you have the continent that was here that is getting closer and closer. So just imagine toothpaste or soap between two bricks, and you start compressing. The toothpaste will when you continue compressing, the toothpaste will be ejected. So that means that everything that was here will be thrusted on top of this continent. This will end up as nappes on top of the continent when the collision occurs. Now you see also, why did I mean, I'm not going to explain you plate tectonics, but I want to show you the history of what we call a true exotic block. So a true exotic block must be born during a rifting phase. And then this block will be drifted because of the mid-oceanic ridge. I forgot to draw it, but here, now your mid-oceanic ridge, a chain of submarine volcanoes will add new basalts. And as you move left and right from the mid-oceanic ridges, the ages of the basalts will become older and older and older. So that means that the basalts that are here are older than those that are here. The youngest are here. And at the end, what will happen when the two continents starts colliding is that all this package of rock here will be ejected on top of the continent as nappes. And when you have the collision here, parts of this will break and will also come on top of this. So you will have all the basalts, fragments or nappes made of basalts, usually coming on top here. The basalts, a basaltic nappe, for instance, would be here. We call them ophiolites. Ophiolites usually are structurally higher than the accretionary prism. Our block is still here in the accretionary prism. And this could be tens to hundreds of kilometers. The horizontal displacement of a nappe is something like several tens to hundreds, even more kilometers, the horizontal displacement. And pieces of the continent might be also, might be break. Continents are brittle in comparison to oceanic sediments and basalts. So you can have big slices that can also come on top of here. So you see, this is the history of a true exotic block. This is what we have in Oman, for instance. Because in Oman, this continent is missing. So we don't have nappes of representing continental lithosphere on top of it. We have what we call an abduction. An abduction is not a collision. This is a collision. In the abduction, the topmost nappes will be the basalts. And in Oman, it's called the semi-ophiolite. And structurally, underneath the semi-ophiolite, you will have, for instance, the Hawazina complex, the Hawazina nappes, which contains Permian and Triassic true exotic blocks. So you see, the history of the so-called exotic blocks of Timor is completely different. And people have been really confused between the two things. You know, once you have a model in your head, it's difficult to take some distance to look at it and go to a new place and realize the model doesn't work for this new place. You always have to make very detailed, close observations in the field. You have to look at the outcrop from the distance. You have to look at the morphology. You know these thrust folds we mapped. Almost every time there is a bend in the river. The river suddenly bends and makes a shape like that, or they can be parallel to the river. Noil Tobe, the thrust fold is in the bottom of the Noil, parallel to the Noil. If it's perpendicular to the Noil will likely be shifted. Why can it be shifted? Because you may have also a small horizontal component. Your thrust may not be like this, it could be like this. So if it's oblique like this, you will have a horizontal component. If it's like this, you have no horizontal component, just a vertical one. But if you look carefully at the topography, you must start thinking and observing the topography. The topography will tell you something. And after, you can make some guesses, some hypotheses, and then you go to the field and you check. Any other questions? Sorry, this was a bit long. This was a bit long, but this is what I wanted you to understand. The difference between Timor has no exotics. This is the history of this is the true history of a real exotic, and we don't have that in Timor.
Yeah. Okay, yeah, thank you. It's quite interesting. Okay, so ya jadi karena beliau berasal dari negara Eropa dan di sana juga di daerah pegunungan Alps dan di sana juga disebut sebagai exotic blocks, dan ini yang beliau gambarkan ini yang disebut sebagai exotic block yang sebenarnya gitu, dan sebagai membandingkan dengan blok-blok yang ada di Timor yang berdasarkan observasi beliau itu beliau tidak ditemukan blok-blok tersebut dari segi tektonik genesanya itu tidak ada di Timor. So there's actually I think 3 more questions from Zoom and maybe 2 from the audience. I don't know about so am I okay
Well,
with
maybe it would be nice to have some question from this audience.
Yeah, sure. Kalau gitu mungkin satu pertanyaan dulu dari audience, baru dilanjutkan dengan pertanyaan yang di Zoom.
Baik, terima kasih atas kesempatan dan waktu yang diberikan kepada saya. Perkenalkan, nama lengkap saya Siprianus Manikale, saya dari Prodi Teknik Pertambangan. Tadi dijelaskan bahwa pernah terjadi kepunahan parah yang pernah terjadi sekitar 252 juta tahun yang lalu. Dan penjelasan Anda mengatakan bahwa dalam penelitian Anda tidak menemukan bukti yang menyatakan bahwa kepunahan itu terjadi di Pulau Timor. Yang menjadi pertanyaan saya, apa batuan atau fosil yang menjadi bukti sehingga Anda menyatakan bahwa tidak pernah terjadi kepunahan di Pulau Timor, dan berapa umurnya sehingga Anda menyatakan tidak terjadi kepunahan itu? Sekian dan terima kasih.
Okay. So basically the question is about your research here in Timor on how you observe there's a ada kepunahan tidak ada kepunahan di Timor maksudnya. Oke, jadi mungkin salah mengerti yang maksud dengan tidak ada kepunahan di Timor. So sebenarnya itu tidak ada batuan pada
use the microphone.
Okay, sorry. Jadi tidak ada batuan ya, yang merepresentasikan awal Trias, gitu. Awal Trias, awal Trias itu tidak ada ditemukan di Timor. Ada dua section di situ yang tidak ditemukan di Timor. Itu bukan berarti bahwa tidak ada kepunahan, tetapi batuan tersebut memang tidak ada di Timor. Jadi entah itu terjadi suatu erosi yang cepat atau tidak ada deposition, sedimentation pada waktu itu. Ada istilahnya hiatus gitu. Jadi batas antara Permian dengan Trias itu awalnya memang sama sekali hilang. Tidak ada batuan terdeposit di masa itu. Bukan yang berarti hal tersebut ya karena tidak ada batuan sehingga tidak ditemukan atau diobservasikan fosil pada masa tersebut. Okay. Namun di daerah-daerah lain seperti di Oman dan sebagainya itu untuk boundary antara Permian dengan Trias itu lengkap ya secara stratigrafinya gitu. Namun awalnya Trias pada boundary atau batas antara Permian dan Trias itu yang tidak ditemukan di Timor. So atau mungkin bisa
maksud pertanyaan saya itu bukti yang menyatakan bahwa tidak terjadi Trias di Pulau Timor.
Yeah. So actually, I think we have the same question on Zoom. Okay, so he was asking why there's a hiatus in the Permian Triassic boundary. You know, the Nerian is not here in Timor, etc. So maybe you can also answer the question. So this is from Isaias Barros from Timor-Leste. Okay. Hello, Prof. Hugo. I am Isaias Barros from Timor-Leste. Okay. Prof. Hugo says hello to Isaias. So his question is, following up, his question is why there are some gaps along the early Triassic. Is this caused by structural gap or only deposition gap? Example is the Smithian-Spathian boundary in the region. So
I didn't understand the point about the Smithian-Spathian.
Okay, so he's asking.
Why there is a big gap?
Yeah, why is this a big gap? Is it caused by structural gap or only depositional gap?
And what about the Smithian-Spathian?
Yeah, example. An example is the Smithian-Spathian boundary.
Yeah.
In the region, maybe are there gaps within the Smithian-Spathian?
Yes.
Yeah. So there are gaps within the Smithian-Spathian boundary. Can you? Yeah.
Can we go? Can I have the slides back, please? So let's go back to Manatuto. Virtual. No, that's the other direction. Sorry. Oh, just past it. Yeah. Okay. Now, if we zoom in, okay, here we have the Permian Triassic boundary, which corresponds to a big hiatus. The late Permian is missing. The beginning of the early Triassic is missing.
Maybe use the mic, Hugo.
Sorry, yeah, thank you. Everyone has its turn. Okay, here we have the Permian Triassic boundary, where the late Permian is missing and the base of the early Triassic is missing. Now, where is the late Smithian? And this is something interesting. You see the colors which are shown here are exactly the colors you will see when breaking the rock in the field, when looking at the fresh rock. So you can see that not all these limestone beds are similar. There might be some slight difference, and this you should notice in the field. And you see here, there is a bed. This you cannot see from your seat, but if I would zoom in, you would see that all this has lots of ammonites. And here there is a white bed. I'm sure you can see it from your place. What is this white bed? This white bed is early late Smithian. The ammonite fauna that is contained exclusively in this bed is early late Smithian. And what do we have on top of it? I should put my glasses, or I cannot read it, but either the bed which is directly above or the second bed on top of it is already late Smithian, late Anisian. So we are jumping here from the late Smithian into late Anisian. That's several million years. So you see another example of gap. How do we know this? That's because before coming to difficult records like this one, we went to expanded records, where the same time interval may be 1 or 2 kilometers thick with continuous sedimentation. And you have all the succession, the complete succession of faunas. of species. Then you have your watch. You have your chronometer. Here, the chronometer is broken. The chronometer is broken, and you need a chronometer from somewhere else in order to detect the gaps in this record. And you see, it is really strange that, okay, at the base we have the early Smithian, here we have the middle Smithian, here we have the early late Smithian, but the Spathian is completely missing. And the early and the middle Anisian are completely missing. And this is a lot of time. So what happened? I think it's probably the same story than the Permian Triassic boundary. The solution is how deep is the water, how deep is the ocean, is the sea on top of the bottom. What is the distance between the surface of the sea and the water sediment interface? Here, the classic, the usual global sea level changes that are due to the formation of the building of terrestrial ice ages. Of course, during the cold episodes, there will be formation of ice. There can be formation of ice. So you will lower down the sea level. And in the case of the Smithian-Spathian boundary, it was something of the order of magnitude of 50 meters. We can deduce this from sequence stratigraphy. So at the Smithian-Spathian boundary, the sea level went down approximately 50, 60 meters. I mean, this is the order of magnitude, not 100 meters or 200 meters, less than that. But if you have shallow seas, if you have shallow water seas, these seas will be completely dried out. So you will start having erosion. If you have no water on top of your basin, you will not have deposition, you will have erosion. So my guess, and here you have two potential explanations. Either there was no more carbonate particle. You know, these limestone are exclusively carbonate. No siliciclastic, no mud, no quartz, no sandstone, nothing, just pure carbonate. So this shows first that they were very distant from the continent and the clastic sources. The clastic sources didn't reach those places. And there are two potential explanations. Either the block was uplifted, or the sea level went down, and there is a third one, maybe both at the same time. So the end result, what you see at the end, the actual record, is a reflection of the two things, of the two potential causes, which are sea level changes and tectonics. Is your continent pushed up with respect to the sea level? You see, it's all relative. You can push up the continent, you can push it up, you can push it down. And at the same time, you can change the sea level because of the climate. And if you change the amount of if you change the surface area of the continent by changing the sea level, you will change climate. And changing climate will change erosion, and so on and so on. So you have a feedback system. It's a little bit difficult to understand, but climate and sedimentation are intimately related. They are not independent from each other. Because if you have, like Timor, a hot, warm, and humid climate, you have a lot of erosion. I was amazed, for instance, in Noil Tobe, in 1991, two colleagues of mine went 2 days to Noil Tobe. And they found a big block of early Triassic, which was 20 meters thick. We didn't see any block that big. But I have the pictures, I have the field notebooks of my two colleagues. And we tried, the first thing we did was, let's look for the block. And I had enough information to know where it was. We came to the place, we looked around, nothing. Nothing, nothing, nothing. So I was really disappointed. And after I realized, all the Bobonaro is just like soap. Every time you have a flood, the Bobonaro slides down, and the blocks, which are brought up, our beloved blocks of Permian and Triassic, which are brought up by the thrust fault and the Bobonaro, they will fall into the river, and they will end up as sand. They will be completely destroyed after a certain number of years. So here, again, to explain those gaps, you have two mutually non-exclusive mechanisms. Tectonics, how thick is your continent here with respect to sea level? And you have climate change. And the two mechanisms may add to each other, or they may subtract to each other. It all depends. You have all the possible combinations. But one thing I am sure of, for instance, if I compare with Oman, a situation which is like this, in Oman, we have blocks of Griesbachian, we have blocks of Dinarian, we have blocks of Smithian, we have blocks of Spathian. There is virtually nothing missing. So that means that our blocks, which we find now in Oman, were always deep enough below the sea surface so that they could record any sediment that would settle on top of them, which was not the case here. My suspicion, but it's only a suspicion, I have no proof for the time. I mean, no, that's not correct. I have real suggestion. You see here that I have a concrete suggestion. Here on this section, no Spathian. And this other section is 20 meters from the first section. It's just laterally only 20 meters from the first section. And here I have one bed of Spathian, which is very rich. It comes, this is this fauna. So within 20 meters, the same bed disappears. How is it possible? It can only be erosion. The only possible mechanism is erosion, and currents, mostly currents, will remove the sediments, will destroy the fossils, and the bed will pinch out. Your fossiliferous bed will pinch out. So it is this bed here, which is really red dark at the top. This bed does not exist anymore, 20 meters left from the section, in a new section, in a section which is just 20 meters apart. This is a good suggestion of erosion by high energy mechanisms like waves, storms, currents, and so on. So I hope this answers the question of Isaias. And the explanation for the long Permian Triassic gap is exactly the same.
Okay, yeah, okay, thank you. Jadi pertanyaan yang tadi disampaikan sama juga dengan hiatus yang ditemukan antara Smithian dengan Spathian boundary. Jadi di dalam Trias awal itu dibagi lagi skala waktunya, ya. Dan salah satunya ada Smithian dengan Spathian itu. Nah batas antara jangka waktu Smithian dan Spathian itu juga ada gap, ya, ada gap antara dua itu, ya, sama halnya juga dengan Permian dengan Trias. Dan dua kemungkinan terbesar adalah pertama adalah tektoniks, ya, jikalau terjadi pengangkatan, ya, dan tidak ada deposit karbonat pada daerah yang lebih tinggi, dan kalau tidak perubahan iklim, ya, perubahan iklim yang mengakibatkan fluktuatif atau naik turunnya air laut itu. Okay. So Okay, yeah, maybe one from Herman Seran. This one is quite interesting. Herman Seran. Okay, it's Indonesian geologist. Oh, okay. Yeah, okay, go. You were saying that the Permian blocks are not really exotic ones, but we encounter several mineralization, copper, gold, etc., potentials along northern portion of Timor Island. In your opinion, are they also not parts of the Olisostrom or in situ deposits, such as in Atapupu and Tanini?
Well, first, I don't know the geology of northern Timor.
Okay.
So if you don't know, no answer.
Okay. Okay.
We also did notice some blocks in Noil Bunu which were heavy mineralized.
Yeah.
This mineralization usually, for instance, gold or silver or such mineral deposits, one well-known type of occurrence is hydrothermal. You may have hydrothermal processes. I mean, especially, I need the slides again.
Tolong tampilkan slide-nya.
And I have to go forward. Okay. You see here, I have no vertical scale for two reasons. I did this presentation in a hurry. And the other reason is those question marks. We don't know what is here. Maybe you have some seismic, I don't know. But such thrust fault systems, as well as, I mean, both normal and reverse faults will allow hydrothermal fluids to go up. The presence of hydrothermal fluids needs a certain load of rocks on top of them. You need here, you need a certain thermal gradient. You need circulation of water. There must be, in order to make hydrothermal mineralization, you need this system to contain water that circulates. And you need certain zones with overpressure or fracturation. Here I didn't show the secondary fracturation. I only illustrated the main fault. But there might be a lot of smaller faults laterally to the main fault. So if you are deep enough here, and the basalts are a good source for minerals. The basalts are known for gold. For instance, in Cyprus, all the gold deposits are linked to the ophiolites and the basalts. So it is not completely surprising to find blocks that are mineralized. It all depends on what is the total thickness here, what is the total thickness of this pile of rocks. My guess is that it's in the order of magnitude of 1 to 2 kilometers, maybe 3. I mean, it's just an order of magnitude. The total thickness here may be something like, let's say, 2 kilometers plus or minus 1, to give a very rough idea. So you may well have circulation of fluids along the main fractures. These fluids will soak the basalts, will leach the basalts, extract the minerals, and they will impregnate the neighboring rocks. I mean, I'm not an expert at thermal mineralization, but I mean, this is basic geology.
Okay,
I hope it does answer the question.
One more question from Zoom, and maybe one from the audience. And okay, so hi, Prof. Hugo. My name is Frederico Santos from the Institute of Petroleum and Geology of Timor-Leste. I have a question for you. How do you suggest the occurrence of gypsum minerals all together with the Permian Triassic blocks within the Scaly K complex?
There are many potential answers. How massive are those occurrences of gypsum? I don't know. I mean, in the field, we didn't see any. If you have gypsum, that means that some evaporite must have been leached by water. That means that somewhere you must have had salt, anhydrite, or gypsum. Gypsum is extremely mobile. Gypsum will be dissolved at low temperature and low pressure and will circulate with the fluids. So basically, anywhere where you have enough, even a mild temperature and a mild pressure, gypsum will be dissolved and will circulate and impregnate other rocks.
Okay, cool. Mungkin dari FKIP biologi ada yang ingin bertanya?
Thank you for your time given to me. I want to introduce myself. My name is Junisa. I am student of the Biology Education Study Program, and my question is, why did you choose Timor as a research location, and did Timor experience an extreme extension based on history at the time? Thank you.
Sorry, I didn't get the end of your question.
Why did you choose Timor as a research location?
Yeah.
And did Timor experience an extreme extension based on history at the time?
Based on extreme?
The history of time. So basically the question is, why did you choose
Yeah,
Timor
this
as a location?
the first part
Okay.
I got.
Okay. The second part I didn't quite understand. It's about extension.
The second part is not clear to me.
Maaf, boleh ulang satu kali.
Why did you choose Timor as a research location?
Okay, this is okay. I will answer this first part, and then we'll discuss the second part of the question, which I did not clearly understood. So why did I choose Timor? Simply because Triassic ammonites are known from this red limestone since the time of Vanner and Welter. That means in the 20s and in the 30s. And they published big monographs, you know. But Vanner and Welter, they already had a crude idea about ammonite biostratigraphy in the early Triassic. And they were smart guys because they already noticed that there was a big gap at the Permian Triassic boundary. They already knew that the Flamengitian, today we call it the early Smithian, was the first limestone bed on top of the Permian. So why did I choose Timor? The first reason is that because of its early Triassic ammonite record. Because I'm interested in the Smithian, I'm interested in the Spathian. And can I have the slides back, or are they already? Yeah, perfect. That's the other direction. Hey, wake up.
Kembali.
Not responding.
Kembali. Terus.
Okay. Here is the answer to your first question. Why did I choose this place? the first answer is that if you go closer to the Australian margin, there is no good early Triassic ammonite record. You will have kilometers and kilometers of sandstone, silt, mudstone. Nothing interesting for me with a very poor fossil record. I'm interested into getting the fossils and identifying them and seeing why, and trying to understand why in the Smithian, if you, for instance, if you move from the western US basin here, why do we find the same fauna here, 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 and here during the Smithian? I told you during the Smithian we have a latitudinal distribution of the species. The ammonites and the conodont, the big oceanic distances between the continent that didn't bother them. They were able to cross large oceans simply passively, being drifted by currents. And what they needed were stepping stones, you see, just stepping stones, so that they could find the nutrients they need, so that they could find the food they need. They were predators. Both ammonites and conodonts were predators. So if you take today's Pacific, the present day Pacific Ocean, the North Equatorial Current, I'm answering you. Hello, I'm trying to answer you. If you take the present day Pacific Ocean, the North Equatorial Current has a speed, is moving from this side towards the west at a speed of 11 meters per second. 11 meters per second. That's very fast. And if you take the embryos, the embryos of ammonites, they were not able to swim. They were drifted by the currents. So they moved, they followed the currents, and they were able to cross the Pacific at that time, which is a huge distance. So we find exactly the same fauna here and in these blocks here and in the Tethys. That's the Smithian. In the Spathian, I told you there are changes according to longitude. Latitude is like this, longitude is vertical. What potential mechanism, and here we have to turn to biology, because basically the geography didn't change. The geography remained the same. Okay, some blocks maybe move 10 or 20 kilometers, but that doesn't change. That's not a big deal. That's no big deal. That doesn't change the global geography of that time. Remember, at the end of the Smithian, you have a drastic extinction. 70% of the ammonid families were extinct. That's huge. That's much bigger than the Permian-Triassic boundary. It is bigger. In terms of percentage, it is bigger, although at the end of the Permian, the number of Permian families was very low. Whereas in the Smithian, the number of families was very high. So you have to use both absolute values and relative values in order to estimate extinction. You know, a percentage will tell you nothing. If you can have 70% of ammonite families or a given clade, a given group of organisms that will go extinct, but what you have to know is how many groups do I have? 70% has not the same meaning if you have 10 groups or if you have 100 groups. You see, that's a big difference. So the idea of this change in paleobiogeography is not related to climate, is at least not related to geographical changes. Same geography. Climate change, you had more or less the same climatic changes in the Spathian and in the Smithian, with ups and downs, cycles between hot and cold climate. So what could be the explanation? Climatic cycles were more or less the same. Geography was more or less the same. Chemical composition of the ocean was more or less the same. So what could have changed? That's a question for the biologists. At the beginning of the Scythian, you have a huge evolutionary radiation. At the end of the Scythian, the ammonites almost went nearly extinct. And at the beginning of the Scythian, you have an explosion. And the ammonites and the mostly the ammonites, they diversified so fast that it is difficult to find expanded records tracking this evolution. You need an expanded record to track this very, very fast evolution and diversification. It's an explosion. And this explosion is not the same within the same latitudes. And this is why the Scythian here is really interesting. It confirms that this part of the ocean, the Tethys, was completely different from the Eastern Pacific in terms of there were a few common species, but very few. Most of the species here and here are different. Not all of them. Fortunately, there are a few common species that allows us to make correlations, but the bulk of the faunas are different. And how can we explain this partitioning of different coeval faunas? Simply, if you keep adding new species with a very quick radiation, all the ecological niches will be quickly saturated. And I'll try to draw a simple diagram illustrating this. If we look what happened during an extinction, we also have to consider what happened prior to the extinction and what happened after the extinction. So time is the x-axis. Time is the x-axis, and y is the species richness. Let's say the number of species, simply. Okay. Before the extinction, you can have something more or less stable, fluctuating around some given mean. Then the extinction starts, and the N-Smithian extinctions lasted 600,000 years. So it's not like the Permian Triassic boundary where everything went extinct during a few hundred thousand years. The late Smithian extinction is a stepwise, longer process. And you have steps like this. So this would be late Smithian. And what happens after? I told you, after the extinction, you have an explosion of ammonite families. You have an explosion of the total number of species if you look at it globally. This is a global diversity curve, not for a specific area, but that's the number of species known from everywhere. And here what happened is you get something like this, or I should say even higher compared to the Smithian. So every species as its own ecological niche. For the biologist, I'm sure you've heard about ecological niche. Do you know what is an ecological niche? Hello, the biologist.
Yang biologi tahu istilah sorry, what was it? Biological niche.
Ecological niche.
Ecological niche. Pernah
Niche.
dengar istilah itu? Niche.
So every species has a preferred environment and will have prey-predator relationships with other species. Every species is part of the food chain. So every species is eating something and will be eaten by something else, unless you are a top predator at the top of the trophic web. So if you add a lot of species very quickly, all the ecological niches will be quickly saturated. You know, ammonites and conodonts were pseudoplanktonic organisms. I mean, at least during their embryonic life, they were pseudoplanktonic. They were passive drifters. So it's very easy for them to go to a new place. They are drifted by currents. But if the place is already occupied by a species which competes for resources, then the last species to come in will not be able to settle. The rule is first come, first served. So if you take a piece of the ocean, if you take a certain volume of the ocean, it can only take a maximum number of species. I mean, the diversification is not an endless process. Diversification will stop when the ecological space, that means the total number of niches, will be completely filled up. So this is why if you take, and it's for the biologist again, but also for the geologist, it's something very simple. If you take at the growth of a population, you take some bacteria and you look at the growth of a population in a petri dish, you will have a curve that is like this, which will level out here at a given number of individuals. That means that the space in your petri dish cannot be occupied by an endless number of individuals, of bacteria. There will be an upper limit. This is called a logistic growth curve. Just replace individuals by different species, and then you have the solution. It's the same model, but instead of looking at the number of individuals, the number of specimens, look at the number of species. So a given ecological space cannot accommodate an endless number of species. It is limited. Simply because of interspecific competition. Competition is a big driver in diversity. And my guess is that the change from a latitudinal pattern, which is clearly dependent from sea surface temperature, to a longitudinal pattern, reflects the increase of species, is a consequence of this extreme number of species and has nothing to do with temperature, salinity, or any other chemical or physical factor. It is simply a pure biological question. I hope this does answer your question.
Oh, that was a really complete explanation. Mungkin jelaskan sedikit menyangkut pertanyaan. Bagian yang pertama tadi mengapa beliau memilih Timor sebagai daerah penelitian di Timor Leste sekitar tahun 2019 dan di Timor Barat tahun 2022. Ya karena kalau kita lihat publikasi pada zaman era Belanda yang mengkolonisasi daerah Timor, khususnya di bagian Timor Barat itu, kalau kita lihat publikasi dari Vanna and Welter sekitar tahun 1920-an, 1930-an. Itu mereka banyak melakukan penelitian khususnya untuk paleontologi juga, yaitu di daerah Besleu dekat Niki-Niki, terus ada juga di daerah di Amarasi, di daerah Baun juga. Nah, itu mereka melakukan penelitian dan lengkap sekali biostratigrafinya. Biostratigrafinya lengkap sekali, namun hal tersebut tidak dikombinasikan dengan stratigrafi. Jadi fosil yang mereka temukan itu, ya mereka melakukan analisa tanpa mengidentifikasi stratigrafi. Jadi dari mengidentifikasi stratigrafi, kita bisa lihat dia berada pada lingkungan atau fauna jenis fosil yang berada pada lingkungan tertentu itu, melihat dari fasies daripada batuan tersebut. Jadi kita bisa tahu, oh fosil-fosil yang ini lebih tua dibandingkan yang fosil yang berada pada bagian atas. Nah itu ya yang menjadi pemicu mengapa beliau juga sangat tertarik sekali untuk meneliti bagian Trias awal itu, karena secara biostratigrafi lengkap tetapi tidak dikorelasikan dengan stratigrafi. Ya, itu makanya kalau kita lihat peta geologi untuk di daerah Timor dan litostratigrafi di daerah untuk Timor itu, kita lihat bahwa di bagian biasanya ditempatkan pada Trias awal. Jadi Permian dan Trias awal itu ada sebutannya hiatus, ya, ada suatu gap gitu. Tidak ada batuan yang berumur early Triassic di daerah-daerah timur. Namun yang seperti yang ditemukan oleh Vanner dan penelitian yang sekarang, kita lihat bahwa batuan-batuan tersebut ada, namun dia bukan awal daripada Trias awal, tetapi pertengahan daripada Trias awal, yaitu pada bagian Smithian dan Spathian. Dan sama seperti tadi, kepunahan yang terjadi pada batas antara Permian dengan Trias, yaitu juga ditemukan, makanya beliau tadi gambar siklus ini, ya. Jadi yang graf yang bagian Y itu adalah banyaknya spesies, ya. Kita lihat bahwa banyaknya spesies dan terhadap X-nya itu adalah time, waktu.
I should add an additional point. One of my PhD students also looked at the size, the adult size distribution of ammonites, and made a compilation of all species known from the Smithian and from the Spathian. And what is surprising is that the average adult size of ammonites in the Smithian is much bigger than the average adult size of ammonites in the Spathian. So this should tell something to every biologist. What is the meaning of size in the trophic webs? You know, in the prey-predator relationships between species in a given environment. Usually, statistically, the bigger will eat the smaller. Okay? If you take, for instance, a coral reef in the, this I did with a colleague from the California Academy of Science. He had a databasis for all organisms, from microbes to whales, from the microscopic organisms to the largest ones, from two Caribbean islands in the Caribbean. And we looked at size distribution, how the size distribution maps onto prey-predator relationships. So statistically, there is a really strong relationship showing that statistically, bigger species will generally eat the smaller ones. There are counterexamples. There are counterexamples, but there are ecological black holes, and they are very rare. You may have smaller species eating bigger ones, but this is not the general rule. This is an exception. So how do we translate this into the early Triassic and the statistically extremely significant change of adult size between Smithian and Spathian ammonites, on each part of this strong, massive extinction of ammonites. If you have fewer species, if at the same time you have fewer species, some of them will have a chance to go higher in the trophic web. Some of them will, because there will be a deficit in interspecific competition, because the competition between the different species, because the different number of species present in an ecosystem, if you have fewer species, this will give perhaps a chance to some species to go up the ladder and to become higher, to become a bigger predator. If you, from the beginning, like with an explosion, with a diversity explosion like the one at the beginning of the Spathian, so in a very short amount of time, all the niches, all the ecological niches are occupied. There is a very strong competition. There is a very strong competition between the different species. And the species will tend to exclude each other first. That's why we change from latitudinal distribution to endemism. We change from a latitudinal pattern to a longitudinal pattern. That's the first reaction. And the second consequence of this is that if you have many species competing between them, there is less chance that some of these species will get bigger. In order to get big, one of the ecological conditions is that you don't get eaten too quickly and that you have a chance to grow larger. Of course, behavior will change everything. Species behavior will also come into the play. There is another potential explanation also for this decrease of average size of ammonites. It could be, but it's an ad hoc. It is really an ad hoc explanation. It could be that fishes, bony fishes are also radiating during the early Triassic. And fishes, they preyed on ammonites. A lot of them have spiny teeth or crushing teeth. It's no problem for them to break the shell. And we do find a lot of shell injuries, shell breakage that are repaired. So if you increase the predation pressure on your species, I mean, there are less chances for the species to become large, to reach a large size. So there are two potential explanations for this size decrease. Increased intraspecific competitions between ammonites, and perhaps, but I don't like it very much, increased predation from fishes, which are also diversifying at the same time. So I hope this puts a different light on the problem.
Yeah, cool. Okay, so ya, jadi kembali ke tadi, bagaimana pada Smithian dan Spathian boundary itu, jadi pada awal Trias awal itu ada dinamakan sebagai Smithian dengan Spathian. Nah, kita lihat di grafik ini tadi ya, banyaknya spesies itu yang Y, terus X ini adalah waktu. Dan lihat pada garis yang paling kanan ini, kita lihat bahwa grafiknya itu spesiesnya semakin banyaknya spesies itu semakin menurun ya dengan berjalannya waktu ya. Namun pada zaman Spathian ini ya terjadi suatu ledakan besar, banyak sekali spesies yang muncul ya dari sini. Jadi banyaknya spesies itu semakin menurun pada sampai akhir daripada Smithian ini. Ya, oke. That's the late Smithian. Yeah. Yeah. Dan Scythian ini terjadi suatu ledakan besar, menyangkut banyaknya spesies. Ya. Ada suatu perubahan, dan kita lihat dari fosil yang ada, ya kita bisa lihat bahwa pada zaman Smithian itu amonit ini mereka bergerak secara lateral, ya, berdasarkan garis latitude. Namun pada zaman Scythian itu mereka bergerak secara longitudinal, ya, longitudinal. Makanya kita lihat jenis spesies amonit yang sama itu pada zaman Smithian itu berada pada garis lateral. Ya, kita lihat mereka ada di samudra ini, tapi juga ada di daerah-daerah Tetis, samudra Tetis dan sebagainya. Namun pada zaman Scythian itu terjadi perubahan. Ya, jadi kita tidak temukan spesies yang sama secara lateral, tetapi kita melihat dia mengikuti pola longitudinal. Ya. Dan satu hal yang menarik lagi, kita lihat bahwa amonit pada zaman Smithian itu mereka ukurannya jauh lebih besar dibandingkan amonit yang ditemukan pada zamannya Scythian. Jadi itu tadi beliau bilang ini suatu pertanyaan untuk teman-teman dari FKIP biologi juga, ya. Perubahan pola jenis spesies yang sama awalnya pada Smithian itu, kenapa dia dari lateral, terus pada saat ke Scythian terjadi suatu ledakan besar, ya, jenis variasi spesies itu semakin banyak, ya, dalam jangka waktu yang cepat, gitu, ya, dalam jangka waktu yang tepat, dan jenis spesiesnya dia mengikuti pola longitudinal. Jadi kita temukan spesies yang sama secara longitudinal di bumi itu. Bukan lagi secara lateral. Yeah, so basically that's a summary of all the question. And I think the time is up here. I think it's very yeah.
Yeah, I think everybody must be tired. At least I am.
Ya, oke. Oleh karena itu saya serahkan kembali ke moderator MC untuk MC untuk melanjutkan acara.
Alright, we have followed an amazing presentation of material from Professor Hugo. Thank you, Professor, as our speaker, and also thank you, Mr. Harep, as our moderator. Hopefully, the material presented can be useful for all of us and add to our insights.
Baik, kita telah mengikuti pemaparan materi yang luar biasa dari Profesor Hugo. Terima kasih kami ucapkan kepada Profesor selaku pembicara, dan terima kasih kami ucapkan kepada Pak Adep sebagai moderator kita hari ini. Semoga materi yang disampaikan dapat bermanfaat bagi kita semua.
Ladies and gentlemen, now we move to the next agenda. It is handover souvenirs. Souvenirs will be handed over by Chairman of Student Association from Mining Engineering. For the Chairman, please come forward.
Selanjutnya adalah penyerahan souvenir yang akan dilakukan atau diberikan oleh Ketua Panitia. Kepada Pak Adep untuk menerima souvenir dan diserahkan kepada
Chairman.
Selanjutnya.
Next, closing remarks from the Chairman of Biology Education Study Program Student Association. For the Chairman, the time is yours.
Selanjutnya adalah kata penutup dari Ketua Himpunan Mahasiswa Pendidikan Biologi. Kepada beliau kami persilahkan.
Assalamualaikum warahmatullahi wabarakatuh. Shalom, salam damai sejahtera untuk kita semua. Yang saya hormati Bapak Profesor Hugo, yang saya hormati Bapak Adep sebagai moderator, dan singkatnya yang saya mulia banggakan semua hadirin pada kuliah umum kita pada malam hari ini. Yang pertama-tama patut kita panjatkan puji dan syukur kepada Tuhan Yang Maha Esa, karena atas segala berkat dan bimbingannya kita boleh mengikuti proses perkuliahan umum kita pada hari ini, kuliah umum internasional kita dengan tema The Permian and Triassic Exotic of Blocks of Timor. Tentu ini merupakan suatu hal yang sangat luar biasa. Ini merupakan suatu pengalaman yang sangat istimewa, karena kita diberikan kesempatan untuk boleh mengikuti perkuliahan yang sangat luar biasa ini. Kami dari Himpunan Mahasiswa Program Studi Pendidikan Biologi menyampaikan terima kasih yang sebesar-besarnya kepada Profesor yang telah bersedia menjadi pembicara atau pemateri dalam kuliah umum kita hari ini. Juga terima kasih kepada Bapak Adep sebagai moderator kita, dan juga selanjutnya terima kasih untuk Himpunan Mahasiswa Program Studi Teknik Pertambangan yang telah mengajak HMP Pendidikan Biologi untuk berkolaborasi dalam kegiatan perkuliahan umum yang sangat luar biasa ini. Harapan kami dari HMP Pendidikan Biologi agar selanjutnya kita tetap menjalin hubungan kerjasama untuk kegiatan-kegiatan dan event-event luar biasa lainnya. Dan semoga apa yang telah kita pelajari bersama, yang telah kita ikuti bersama dalam perkuliahan umum kita pada hari ini dapat berguna untuk kita amalkan, untuk kita implementasikan dalam kehidupan kita setiap hari, sehingga dapat berguna bagi sesama kita, bagi kelanjutan kehidupan kita. Oke, mungkin ini saja penyampaian dari saya. Jika ada kekurangan dan kesalahan, saya dari tempat ini memohon maaf yang sebesar-besarnya. Terima kasih.
Closing pray.
Selanjutnya doa penutup.
Marilah kita menyiapkan hati dan batin kita untuk berdoa. Izinkanlah saya membawa doa ini sesuai ajaran agama Katolik. Dalam nama Bapa, ya Allah Tritunggal Maha Kudus, Bapa, Putra, dan Roh Kudus, kami lambungkan puji dan syukur berlimpah atas cinta dan berkat yang telah Engkau limpahkan kepada kami. Pada kesempatan yang berharga ini, kami secara khusus ingin menyatakan syukur untuk penyertaan dan bimbingan-Mu selama kegiatan perkuliahan tadi. Kami dapat mengikuti kegiatan ini dengan baik. Kami ingin selalu merasakan nikmatnya berkat daripada-Mu, maka kami mohon semoga perkuliahan ini boleh menambah wawasan kami, mengasah kemampuan kami, dan menambah kebijaksanaan kami. Biarlah dengan ilmu yang telah kami dapatkan ini, kami selalu mewartakan nama-Mu dalam tutur kata, tindak laku, dan semangat hidup kami. Semoga kami boleh menjadi generasi yang berguna bagi bangsa dan bagi gereja-Mu dalam mengamalkan kebaikan-Mu. Semua doa dan harapan ini kami sampaikan kepadamu lewat Kristus Sang Guru Ilahi. Nama-Mu yang kudus senantiasa kami puji, kini dan sepanjang masa. Amin. Dalam nama Bapa.
Next, we will do a photo session together. For Professor Hugo and Mr. Adep, please come forward so we can do the photo session together.
Selanjutnya kita masuk kepada sesi foto bersama. Kepada Pak Adep dan Profesor Hugo, mungkin bisa berdiri di tengah sini, Mister, to take a picture with all participants. So can you stay here? Yeah. So ambil, ya maksudnya bapaknya hadap sini, nanti diambil dari sana biar sekali. Mungkin semuanya bisa berdiri. Tolong ini.
Selanjutnya sesi foto pemateri bersama mahasiswa dari program studi pendidikan biologi. Bagi